Okay, so here we have an example of using those relationships that we talked about between a function and its derivative, but not graphically. So here we're given the equation of a function. So see that we have an amount of water in a holding tank, and this function tells us the volume or the amount of water there. So it asks us to figure out whether the amount of water is increasing or decreasing at a particular time. So notice that our independent variable is time, measured in minutes. So what we want to do is first compute the derivative, and then the value of the derivative will tell us whether the volume is increasing or decreasing. So we just use our formula that we've been using for computing derivatives. So this is the limit as h goes to 0 of v of t plus h minus v of t over h. And then we plug in, so here we plug in t plus h. And then we have to also subtract 2t squared minus 8t. Okay, and so with this type of limit, we usually multiply out and try to cancel. So multiplying this out, we get t squared 2t times h plus h squared. And then if I distribute that negative 8, I get this, and then I'm going to distribute this negative sign, so plus 8t. Okay, so we do actually get some cancellation already, so this 8t cancels with this negative 8t, and then I'm going to distribute that 2. Okay, and then we minus 8h minus 2t squared. Okay, and then we get that the 2t squared cancels with the minus 2t squared, and then all of the other terms that are left have an h in them, so I'm going to pull out an h. So we'll be left with this over h. These guys will cancel, and then I can just plug in h equals 0 now, once I've canceled. And so this will just make this term 0, and we'll get 4t minus 8. Okay, so that is our derivative, so v prime of t. And if we want to evaluate it at 1, we can just use our formula to evaluate it at that point. So when we plug in 1 to this formula for v prime, we get 4 times 1 minus 8, so negative 4. Okay, so that means that the derivative at 1 is negative. And what that means is that the function is decreasing there. So this is less than 0. So let me actually write this out a little nicer. So this is negative. So v of t is decreasing at t equals 1. Okay, so all we had to do was plug in the number that we cared about, or the time that we cared about, and check whether it was positive or negative. And that will tell us whether the function is increasing or decreasing. Okay, and so similarly here we're asked for whether the function is increasing or decreasing at 5 minutes, and we've already done all the hard work of finding the formula for v prime. So I'm just going to copy that down, and we just plug in 5. So we have 4 times 5 minus 8, which is 20 minus 8, which is 12. And so that's positive. So, so the function v of t is increasing at t equals 5. Okay. And then it asks if the volume of water is changing faster at t equals 1 or t equals 5 minutes. And so remember, this is determined by the magnitude or the size of the derivative at each of them. So v prime of 1 is equal to -4. So that means the absolute value of that is 4. And then v prime of 5, well, this was already positive, so it will be 12. So since this is bigger, that means bigger, so the function is changing faster at t equals 5. Okay? Okay, now this asks is the volume of water ever not changing? If so, when? So we say that the volume is not changing if v prime of t is equal to 0. So if that were to happen, that means, well, the derivative is equal to 0, and the derivative tells us how fast the volume is changing. So 0 means it's not changing. Okay, so we can solve this by just using our formula that we found for v prime, which is 4t minus 8, and then we solve for t. So just solve for t, and we get t equals 2. Okay, so that means that the volume is not changing at t equals 2 minutes. So if this seems a little weird to you to say that the volume is not changing at a particular moment, I think it makes more sense in the context of, like, say you were talking about the velocity of a train, like on, oh god, am I gonna try to draw a train? I guess so. Okay. I don't know, they have a chimney. I don't know what trains look like. Okay. Anyways, so you have a train on some train tracks, right? So it has to stay on the tracks. And if this train were to try to turn around, it would be going, say, this way, and it wanted to reverse and go back in the other direction. There's a moment, like a particular moment, where it actually has to stop moving in order to turn back around, right? So you can think of that being the moment at which the function is not changing, right? So there's just like that tiny little moment where they have to stop and then go back and reverse in the other direction. Okay. Now there's one more thing we have to talk about, and that is higher order derivatives. So we've been talking about just a regular derivative, and we can actually define or we can just take the derivative of a derivative, and so that gives us what we call a higher order derivative. So we can take the derivative of the derivative. So, and we call this the second derivative. Okay, so the derivative is a function, and we can take the derivative of a function. So we can just actually keep doing this. So we can get a second derivative, we can get a third derivative, and so on. Let's talk about the notation for the second derivative. So we would have, well, we have our first derivative, right? And then we want to take the derivative of that. So I put the prime on the outside of the parentheses to mean that we're taking the derivative of what's inside. And some nicer notation is just to do 2 dashes or apostrophes there, right? And so we read this f double prime. So for the regular derivative, we read it f prime. In this case, we call this f double prime. And we can also, so the Leibniz notation, I know we haven't used this much yet, or maybe not at all, but we will. And so, yeah, the Leibniz notation for the second derivative, we have the notation for the first derivative is df over dx. And then we want to take the derivative of that, and the way we denote that is d over dx. This means take the derivative. Of what's in the parentheses. Okay. This d over dx. And maybe I'll just for completeness, we'll write this. This means the derivative of f. Okay. So we want to take the derivative of the first derivative. So now that we have the second derivative, we refer to the regular one as the first derivative. Okay, and so to sort of simplify this notation, it will look like d squared f over dx squared, like that. How you can remember this is that, well, first of all, if you were to combine these two, or if you were to imagine like multiplying them together like fractions, what you would get is a dx and a dx, so focusing on the denominator. So we get 2 dx's, so we rewrite that as dx squared, like that. So that's the denominator, and then in the numerator we get a d and another d, so we write those as d squared, and then the f is tacked on the end. Okay, so that's how you can, try to remember the notation. The reason why Leibniz notation is so nice is because it sort of behaves like fractions, so we can use the rules that we already know for fractions to help us remember notation for different things. And actually, it's really helpful when we learn the chain rule to remember the chain rule. But we will not talk about that for a while. Okay, so thinking about this in the context of position and velocity, which we've been talking about. So we know that the derivative of position is velocity. Then the second derivative, which tells you how fast the velocity is changing. So think for a second what you think the second derivative might tell you. So the second derivative of position, which tells you how fast the velocity is changing, is the acceleration. Right? Okay, so these are really useful because we have a lot of intuition about velocity and acceleration. right? And so it can help to always keep those examples in mind to have a better idea of what these quantities are actually telling you, right? So, okay, so we can also just keep going with this. So we can take the derivative of the second derivative, and we get the third derivative, the third, fourth, fifth, as many derivatives as you like. And so for the third derivative, the notation, so derivative of the second derivative, we just add another apostrophe there. So sometimes I'll say this f triple prime. Okay, and then the Leibniz notation, basically same idea. So the derivative of our second derivative is the third derivative, so we just have a 3 now as our like sort of power. Okay, and then fourth derivative. At this point, the notation here changes a little bit because we can't just keep adding primes because that will just get out of hand really fast and hard to keep track of. So at this point, we'll switch to writing it as f and then a 4 in parentheses. So that it doesn't look like it's f to the power 4. So you don't want it to look like an exponent. So we put it in parentheses, and that will be our fourth derivative. That's how we denote that. For the Leibniz notation, it doesn't actually change though. So this is already well equipped to handle the fourth derivative. So this is just over dx to the 4. Yeah, like that. And then you can just continue in this fashion. Okay, so don't forget to take the comprehension check. I think that's all for today.